Okay, so you can't really have managed to survive 2018 without having heard of these particular vulnerabilities. If you have not heard of these, you've been under a rock since the 4th of January. So why am I talking about them? I'm talking about them because these are probably the most interesting and important and far-reaching software vulnerabilities, not really software vulnerabilities, hardware vulnerabilities that we've seen in 20 years. So what I want to do is to explain a bit about what the problem is, how that interacts with operating systems, and the upshot of this at the end is, why is my CPU 50% slower than it was 3 weeks ago? Yeah, it's basically, it is that much. Depends on what it's doing, actually. So there are lots of people who deserve credit for this, and I'm not one of them. I'm not really a security person, I'm not really an operating system person, and I'm not really a computer architecture person. I'm really a networking person, but I've spent enough time in all of these areas to have the overview of everything, so I'm probably an okay person to talk about it. The people who discovered the vulnerabilities, the list is here. The people who have been working on mitigating these vulnerabilities, the list is a lot longer. And the important thing although these guys deserve a lot of credit, mitigating these sort of problems is a lot harder than discovering them. On the other hand, these vulnerabilities took 20 years to discover, so it doesn't mean it's that easy to discover. They're sort of things which are obvious with hindsight, but not in advance. So what's the problem here? These are basically vulnerabilities in modern CPU designs, and they're due to the interaction between speculative execution in the CPU, and I'll explain in a minute what that is, and side effects. And a side effect is something that is not supposed to happen, but it turns out you can observe it anyway. The history of this is that the first of these vulnerabilities was discovered in June of last year by a guy working for Google's Project Zero. Google then communicated with Intel and ARM and so forth, and they started to get mitigations in place. Some of these mitigations seemed unusual to some other researchers who had done a little bit of prior work in this, and they started to look at the same thing because they could see the changes. And they went on to discover other vulnerabilities. All of this stuff was embargoed until January the 9th. It wasn't supposed to be public knowledge then because they are so wide-reaching. Unfortunately, because of the way the Linux kernel development process works, clues were starting to creep out through things that were being committed to public repositories, and the register published on January 4th. So the embargo got broken, and everybody then scrambled to try and coordinate a release of information about these particular vulnerabilities. So the effects of this, it's not minor. You need to modify the CPU firmware on your CPU. You need to modify how the virtual memory system works in your operating system. You need to modify all of your compilers, and I mean all of them. You need to modify your web browsers. You need to modify the hypervisor for your virtual machine. And these will only mitigate most of these, but not complete things. And the performance hit from doing this is going to be between 5 and 50%. And that doesn't necessarily get everything. The only real solution is to replace your CPU. Everything else is a workaround, and even replacing the CPUs with stuff that's going to come out in the next year is not going to be a complete solution. So any time where you talk about replace your CPU, things are not actually a great situation to be in. I'm doing my best not to exaggerate the importance of this stuff, but it actually is pretty wide-reaching. Okay, so I'm going to lead you through a long story, because there's a lot of detail that we're going to have to go through to actually understand what's going on here. For those of you who don't have any background in this, I apologize if it gets too much. Please just feel free to leave if you wish. But we'll go through quite a lot of detail, and I'll try and make it accessible to you and so forth. So first of all, I'm going to talk a bit about speculative execution, which is basically what it is and why your CPU needs to do it. I'll talk a little bit about virtual memory, just enough to understand the Meltdown vulnerability, but no more. And then we'll actually talk about the 3 vulnerabilities. So there's one called Meltdown, which is, I think, the easiest to understand of the vulnerabilities, and perhaps the most egregious. Then there's 2 others which are variants of Spectre. We call them Spectre 1 and Spectre 2. And I'll talk about those and what people are trying to do to mitigate these vulnerabilities. So at any time, feel free to stop me and get me to go back and explain and so forth. We've got, I think, a 2-hour slot, and I'll probably end up using much of it. So, first of all, speculative execution. So, once upon a time, many years ago, what a CPU looked like is that the CPU would, on the first clock cycle, it would fetch an instruction from memory. On the second clock cycle, it would decode the instruction. On the third clock cycle, it would actually execute it. And so this looks something like this. So every time your clock ticks, one instruction is being fetched from memory. The next one will fetch, and the next one will fetch, and so forth. So what you have here is a pipeline with essentially 3 instructions in the pipeline. The first instruction is being fetched, then it will be a clock cycle later, it will be decoded, and it'll be executed. And then you end up with some parallelism as well, because an instruction can be being fetched, decoded, and executed at the same time. And so this is sort of typically how a CPU would work mumble years ago, a long time ago. Okay, so this is the model of a CPU you got in your head. It doesn't look anything like this today. Okay, but unless you sort of start with something simple, then it's hard to understand why we made things much more complicated. So a modern CPU, you've got many cores, and each of them is clocked at something like 3 gigahertz. Okay, so you all know that from the promotional literature for laptops and things. What's less obvious is that the memory latency. So the memory latency is when I want to fetch something from memory, how long does it take for me to get it? Okay. This is separate from memory bandwidth, which is how many bytes per second I can transfer from memory. Memory latency is, I want something now. How long have I got to wait? And the answer is about 100 nanoseconds. Okay. Now, memory has improved in performance over the years, but nothing like the way CPUs have improved in performance. So if we want something from memory and we don't have it, we're going to have to wait something like 300 clock cycles. That's 300 clock cycles when we could be doing something else. Okay. So if you had to wait 300 clock cycles every time you actually wanted to execute an instruction, your CPU would be the performance it would have been back in 1990. So we don't really want to roll back 25 years of CPU design. So how do modern CPUs go fast? And I gave you a bit of a whirlwind tour about what CPUs do to go quickly, just enough that you can understand what's going on with the security issues here. So these are the sort of the specs for a modern Intel Core i7 Xeon CPU. And what it has is inside the CPU die, there's multiple layers of cache. And there's the L1 cache, which is very close to the CPU core, very fast memory, very expensive memory. You don't have very much of it. And even to get to the L1 cache, it still takes us 4 clock cycles. That's 4 cycles when we could have been running instructions. And a modern CPU will actually execute more than 1 instruction per clock cycle. So even going to the L1 cache is quite expensive. And that's the best possible thing you can do. The next thing is there's a second layer cache, which is a bit bigger, a bit slower, and it takes about 10 clock cycles to get there. And then your CPU will typically have quite a large layer 3 cache. And the details of why these differ and so forth, I'm not going to go into today. But you should have in mind that even if it's in the CPU cache, not in RAM, it can still take you between 40 and 75 clock cycles to get it. So that's if it's in the cache. If it's actually in RAM, you've got up to sort of 100 nanosecond sort of time. So you're looking at 300 clock cycles. So you really depend on data actually being in the cache if these are going to go fast. Otherwise, it's going to be really slow. And we're talking like 100 times slower. OK, so what do CPUs do to go fast? First of all, they have a cache.
One question. So this is the latency of loading memory location into a register?
Yes. So I was just about to say, the way CPUs go fast is, first of all, when they fetch data, they fetch it a cache line at a time. They don't fetch 1 byte at a time from memory. A cache line is 64 bytes. And they do this because actually the throughput from RAM is not too bad. It's the latency. It's how long it takes to go that far, latch address lines, and start reading stuff back. So they'll read a cache line at a time from RAM. So that means that they'll get multiples of 64 bytes into at least the layer 3 cache, and generally speaking, if you're going to access it or move up to the layer 1 cache. The second thing to bear in mind is that even reading from the layer 1 cache, which is the best possible place you can read to other than a CPU register, takes 4 cycles, and the layer 2 is 10 cycles. So to make this work, to actually keep the the bit of the CPU you want to keep going, the stuff that's doing maths and stuff, you're going to have a long pipeline. You're going to have to ask for something long before you need it. And so typically we're looking at pipeline depths of maybe 20 instructions or something like that. So you've got to ask for it long before you need it. And that's to mask the fact that even the cache is not that fast. If you have to go to RAM, you're still stuck, because it's much slower than that. And then the third thing that's important is that your CPU's arithmetic and logic unit, the thing that actually does what you want to do things with, the maths and things like that, that operates on CPU registers. So registers are special variables within the CPU itself, and it, generally speaking, will only do things like arithmetic on register values. And they're actually within the CPU core, and they are fast to access. Okay, so this is sort of background. If you get this kind of lay of the land, you're in the right place to start to understand what's going on here. If you want to actually look at what's going on inside a modern CPU, you've got lots of different pieces here. There's not much I'm going to explain here other than, first of all, the arithmetic and logic unit, there's a lot of parallelism here. We can actually execute multiple instructions at the same time on the same clock cycle. And that's one thing we do to go fast. The other thing is to note that there's this reorder buffer and scheduler and things. So instructions come in and they're decoded into micro operations. So you might have heard people ranting about how bad the x86 instruction set is and stuff like that. It doesn't really matter, because internally it doesn't do that anyway. It decodes stuff into its own internal micro operations, and that's what it runs internally. So what the CPU does inside is completely different from what it does outside. And so there's basically a queue of allocating stuff into here. There's a reorder buffer that can shuffle instructions around, and I'll explain in a moment why you want to do that. And then a scheduler that schedules stuff onto these. And all of this stuff can then happen in parallel. And that's sort of part of how you make a CPU go fast. So the pipeline to make this work is quite deep. And so these vulnerabilities, we can sort of trace them back to, actually, how far back do you think these vulnerabilities go? Any guesses? We got an idea of what the first CPU was to suffer from these vulnerabilities? Some of you aren't actually old enough to have been born. It's the Pentium Pro from 1995. The vulnerabilities have been in our CPUs since then, and we hadn't noticed, which is kind of scary. So this comes from Microprocessor Report in 1995, and it just shows the pipeline for a Pentium Pro. I'm using this one because it's the oldest and therefore the simplest possible diagram I could show you. The more modern ones are much more complicated. But you can see that basically what's happening is we're loading things into the pipeline. They're going through the instruction cache. They're going through decoding. There's some scheduling process that goes on inside the CPU. Execute only happens here. And then we retire, which means we're done with those instructions. We can make their side effects vulnerable to everybody else. Side effects visible to everybody else. And then if you actually have to load anything from cache, then you would have to do all of this as well. So what this basically says is even on a Pentium Pro back in 1995, the best possible pipeline was 12 clock cycles to get through the pipeline. More typically with 18, and that's if you didn't have to load anything from cache. Otherwise, it was longer still. And modern CPUs only make this worse and more complicated because they're trying to mask those latency effects much more heavily than was ever done before. Okay, so that's sort of a little bit about computer architecture and so on to sort of set the scene here. You're good with that so far? Okay. So I'm going to use an example which comes from Ibn Upton, which basically shows why modern CPUs need to do speculative execution. Okay. So what I'm going to do is use a simple example like this. The reality is that we're really talking about stuff being in x86 assembler, and even then we're really talking about in the micro-ops for x86 assembler. But this is basically illustrates the same point, but with stuff that looks a bit more high level. So here we have 6 arithmetic operations. And if we want to run this on a CPU, then for a simple CPU, if we want one operation per clock cycle, it's going to take us 6 clock cycles. So if your CPU did that all the time, it would be quite slow. And so Intel and AMD and ARM and so forth have been doing their best to make things go a lot faster. And they do that because you can't clock silicon any faster than you could 20 years ago. They mostly do it by being smart in the architecture. So the first thing that CPU manufacturers did was to make their CPUs superscalar. How many of you have heard of superscalar? Okay, not many. So superscalar basically means you can run more than one instruction at the same time. So if I go back to this diagram, there's multiple arithmetic and logic units. So multiple of these can be happening at the same time. And that's how you go fast. So superscalar simply means we've got parallelism inside here in the pipeline. So if we just run one instruction per clock cycle, we end up with quite a slow execution. So what we can do is we can say, well, okay, suppose we've got a fairly primitive CPU. It can just run 2 instructions per clock cycle. Real modern CPUs can run a lot more. Typically something like 4 integer instructions and multiple floating point instructions at the same time in the same clock cycle. But I'll just use 2 as an example in these slides. Okay, so if we do 2 operations per clock cycle, we can complete in half the time, and that's good. Your CPU goes twice as fast. So you get away with this because there's no dependency between T, A, and B, and between U, C, and D. So we can run them at the same time. It doesn't matter. There's no dependency between them. Unfortunately, if you were astute, you would notice that there is a dependency between those 2. We calculate V, and then we use it, which means we can't do those at the same time. It's not possible. You need to actually calculate it before you use it. And so we can't actually run all these in parallel. What we have to do is that. Yeah, we have to calculate it before we use it. And that means that now we've got empty slots in our instruction pipelines. And we spend all that silicon on being able to execute multiple instructions at the same time. And then data dependencies mean that we can't use them. Oops, now it's going to go slow again. So what can we do? Well, we can look at these instructions and go, that one doesn't depend on V. So V doesn't depend on that, that doesn't depend on V. Maybe we can just move that one up. And so now we're doing out-of-order execution. We've looked at all the work we can do, and we've shuffled things around to figure out what things depend on what other things, and we've done them out of order. And that means we can now execute lots of stuff in parallel. And that means your CPU goes fast. Okay, so far so good. What we've described so far is a superscalar out-of-order execution CPU. The problem is that this sort of thing is kind of like a dragster. I mean, it's very fast in a straight line, but it really won't go around corners. So what do I mean by corners? I mean, a corner is an if statement, or a while statement, or somewhere where the execution just doesn't go in the direction you can predict in advance. We can load stuff in with our long pipeline, we can keep all those execution units busy, and we can go really fast in a straight line. But if we don't know where we're going next, what do I load in my pipeline? Don't know. It depends on the result of that if statement. I haven't calculated it yet. So to make modern CPUs go quick, the first thing they do is a thing called branch prediction. And so what they do is they guess which branch is going to be taken next. And exactly how they guess we'll come back to in a little while. But for now, just assume they guess, and they mostly get it right. So they'll guess which branch is going to take. They don't know the answer to the conditional yet. So they don't know whether the if statement is going to be true or false. But they'll guess and say, well, probably this time it's probably going to be true. So I'm going to start executing. And well, what they'll first do, they'll start loading the pipeline. So at least keeps the pipeline full. The thing is, that's actually not quite enough. But anyway, if they guess right, then great. We were loading the pipeline up. It's all there when we want to execute the instructions, and we're happy. If we guess wrong, then we go, oops, we got that one wrong. We've got to flush all that stuff out of the pipeline and load what we should have loaded and carry on again. So every time your branch prediction gets it wrong, you take a performance hit. Of course, the performance hit is not worse than you would have taken if you had just stopped and waited for the conditional. So most of the time you get it right, it's good. Every now and then you get it wrong, and we take a performance hit. Hopefully that doesn't matter. Now, this isn't quite enough. All this will do is keep things in the pipeline. But remember how slow memory is? We can't really afford to wait for memory because we can only get so much stuff out of that pipeline. So what we have to do is to keep not just loading the pipeline, we actually have to start executing stuff that we don't know whether we should be executing. And that's called speculative execution. So the idea is we'll guess which branch we're going to go down. We'll start loading up the pipeline. When the pipeline is loaded, we're going to actually start executing that pipeline too, even though we don't know we should have gone that direction. And that's great if we guessed right. And if we guessed wrong, well, we've got to undo the effects of all of that computation we just did and go down the correct branch. And so what CPUs do is that they start executing, they carry on down a branch, they'll keep all of the results that have been calculated internally in the CPU, they won't make them visible to anything else. And if they've guessed wrong, they'll just flush all of that and say, it didn't really happen, nothing to see here.
What is a cache miss?
Oh, a cache miss. It's when you go to fetch something from memory. If it's in the cache, you get it back from the cache, so it's quick. If If it's not in the cache, you have to go to the next layer of cache or the next layer of cache. If it's not in the layer 3 cache, then you actually have to go and really fetch it from RAM. And then you spend that 300 cycle delay that we're talking about. Okay.
So when you say that you undo everything that you did?
I've got an example. So shall I show you the example, and then if that hasn't explained it? Okay. So here's an example of execution without speculation with an if statement. Okay. So first thing to note is there's data dependencies between all of these. Okay. So we don't know the value of v until we've calculated this. Okay. And then these also have data dependencies between them. So we can't execute these in parallel, we can't execute these in parallel, we can't do these until we know whether this is true. So that's sort of the starting point. So that's going to be slow. It means we can only use one of our many parallel pipelines through our CPU, and it's going to be slow. So speculative execution says, OK, we're going to guess that v is 0. Okay, we'll guess it's 0, so we'll move those instructions up here. And I've given them different names because these are not the, that should be underscored there, that's an error. But these are not actually going to appear to be visible to anything else yet. So there's some hidden stuff here to do with register renaming and things, which I'm not going to talk about. But so we take that stuff that was inside the if statement, we put it up here, and we calculate and put these things in these temporary registers. Okay, so it's calculated, but we don't know whether we need it yet. And when we finally get the condition here that we know whether it's happening or not, then we basically just rename those registers to things that are visible. And if we don't take the if statement, then these never become visible, so it doesn't matter. You know, who cares? So the key is that the results are only available to anything else in the code if the condition was actually eventually true. And if the condition is not eventually true, we just flush the results. It doesn't matter. Who cares? We calculated them. We used part of our parallel pipeline to calculate them, but we couldn't have used that for anything else anyway, so we didn't waste any time. We wasted a little bit of electricity calculating them without needing to, but who cares? So that's what happens with speculative execution. That is what your modern CPU actually does to go fast. It runs a lot of parallelism, it has a long pipeline, it prefetches stuff like crazy into the cache and then into the CPU pipeline, and it does speculative execution. It guesses which branch you're going to take and starts running it, even though it doesn't know whether the branch is true or not.
Maybe worth noting that the abandoned flush state, they cost you energy, and so that's why old crummy phones don't suffer from this problem, because they don't do speculation in this way, because they want to elongate the battery life. So going faster was not so important for a phone, the battery life was more important. So low-end ARM processors are used because they don't do this.
But this is partly why your expensive Xeon CPU burns 100 watts.
What if you try to fetch something from the memory in the speculative execution part and it hasn't arrived by the time you go down? So what happens? Can you cancel out the...
I'm going to have an example of why this turns into a vulnerability. That may answer your question, I'm not sure. Before I talk about that, though, I'll be good on what's happening with speculative execution here. Because then I'm going to take a very brief aside into how virtual memory works, and then we'll talk about Meltdown.
I just have one question. So when you say that you flush everything, does that...
You flush these temporary variables, yeah?
So if you change the cache due to the speculative execution, do you go to the previous state of the cache or not?
So the stuff stays in the cache. So if it got loaded into the cache by speculative execution, it will still be in the cache. On the other hand, it shouldn't be accessible if it wasn't meant to be accessible. But that's where these vulnerabilities come from. Okay, so we'll show you in a second why this is dangerous. But it's what all modern CPUs do, except for crummy ones in John's phone. Okay, so you said you guys didn't really know very much about virtual memory and how that works. So I'll give you a very, very brief primer as to what's happening with virtual memory. Okay. I'm going to give this as an example on 32-bit Linux. It's quite different on 64-bit Linux, and it's different again on Windows. But this gives you a general concept of what's going on with virtual memory. So when you run a program, it thinks it owns its whole address space. Okay. Your program can load stuff. If you're writing in C, you'll be using pointers, and you'll be loading stuff in and out using those pointers, and they are memory addresses. They're virtual memory addresses. They're sort of fake memory. They're what your process thinks it actually has as its address space, but it's not really the addresses of the actual physical RAM in your machine. So your process thinks it has this address space. In between virtual memory and the actual physical memory, there's a thing called the page table. And the page table is a mapping between which page of virtual memory and which page frame in physical memory correspond to each other. So not all of your program that's running has to actually be in real memory at the same time. Some of it can be out on disk and so forth, but let's not worry about that. For now, the main thing is there's a mapping between virtual memory and physical memory that the operating system maintains in order to share the physical memory between different processes that are running. Okay, so the two things that are important here. The first is that we notice that kernel memory is in the process's virtual memory address space. So what happens is if the process is running, if your code is running and it tries to read and write from stuff in its part of the address space, there's no problem. If it tries to read or write to kernel memory, which is within the same address space, there'll be a hardware trap. The hardware will say, you can't do that, and because there's a page protection bit on those pages which says you cannot access that memory. You're prevented from doing it. And obviously this is important because if you could read or write all the operating system's secrets, there's no protection between processors, which means that your web browser can own your machine or whatever. So the way we rely on keeping the operating system separate from user space processors is by page protection. While your process is running, it can't access anything beyond its part of the address space. This is forbidden. So why do we bother putting that in the virtual memory space in the first place? Seems like an odd thing to do. Well, the reason is that when we switch into kernel mode, for example, we ask the operating system to do something for us via a system call, or an interrupt happens, a network packet arrives, and the operating system actually has to do some work. It will context switch into the kernel and start running in the kernel. And if this is in the address space that's already loaded in the page table, we can do those things quickly. Okay? We can do a system call to find out what the current time is and come back again pretty fast because we don't have to switch the page table. We do switch from user mode to kernel mode, but the kernel can access its own code and the user space code, and you can switch back and forward pretty fast between the two. Obviously, if we switch from my program running to the kernel to John's program running, then we do switch the page table at that point, and that's a more expensive operation. And we'll talk a bit more about why that happens later. But if I only want to be able to handle an interrupt in the operating system, and it's busy running my code and suddenly a network packet arrives, and the operating system needs to go and handle the interrupt, there'll be a context switch into kernel memory, and we'll start running code in here. It'll finish doing what it needs to do, and it'll context switch back and carry on running your code. And because it's all in the same virtual memory space, that's relatively quick. Okay, so that's all you need to understand now to understand where the meltdown vulnerability comes from. Okay, you're happy with this concept? I've hidden tons and tons of detail on virtual memory just to give the general concept.
Why would my process handle a network packet?
It doesn't. The operating system does. But the operating system has to handle it on some CPU core. And the CPU core isn't free. It's got to handle it on a core that was doing something else, like running your program. So the interrupt will be handled on some core that was usually previously busy doing something useful for you. And so the hardware interrupt causes the operating system to start executing code, and then it will come back again. You don't see it happening. It's hidden from your code. But it has to do it. Every time a block of data arrives from the SSD, every time a packet arrives from the network, every time you hit a key on the keyboard, it has to interrupt into the operating system and run some code. Okay, so meltdown. The example for this is very similar to what you just saw. Okay, so here's the example. We've got some stuff that executes off registers, and then we've got a conditional, and we've got some other stuff that executes, okay? So it looks just like the example you saw. So you can guess what's going to happen with speculative execution. It's going to say, oh, maybe V is 0, so I can shift that up there. Okay, that's what's likely to happen. Now, if I actually run this code, note that this code tries to read from an address in kernel memory. So that's your process trying to read from something in here. What's going to happen? There'll be a hardware fault, which will normally terminate your process with extreme prejudice. Okay, so when that's meant to happen, the code will fault. and will normally be terminated, although there are some other things that can happen. So what should happen is, this is an illegal access, it will fault, and this code will not be run. That's what you would think would happen. That's the same thing that should happen. So what actually happens on a modern Intel CPU? What happens is, first of all, it does speculation. It says, oh, we could run that all up here because we've got a spare pipeline, so why don't we do it? And it starts to run it, and it loads this into here, and it does all this stuff, and we'll worry about that in a second. So now, this is running this speculatively. So what happens when it tries to do this? Normally it would fault, but we don't know whether we should be running this branch at all. Maybe we should, maybe we shouldn't. We can't fault there. We can't fault at that point because we don't know whether the code is actually going to do something bad or not. It has the potential to do something bad, but it will depend on whether v was 0. And we haven't got there yet. Okay.
But shouldn't the kernel memory be only accessible in the kernel mode?
Yeah,
So
it should.
if it's a user program, then it shouldn't be able to access any point in time.
Yeah, but how does it tell that it's going to this point? Basically, it needs to terminate your process at this point. But remember, this memory is in the address space. It's just there's a protection bit set. And so the question is, where does it check that bit? Even if it checks it here, it can't fault here. Okay? Because it doesn't know whether you're actually going to run this code, because we haven't got to the conditional yet.
It should remember that it will have to fault if you take that branch.
So that's what it does. Okay? So if v is 0, it will fault here. Okay? So that means that this never happens. So the values that were calculated in here are discarded, and so there's no problem, is there? So Intel thought. So that's what's meant to happen. Okay. That's what was the design spec for Intel CPUs for the last 20-something years has assumed is a reasonable thing to do. Okay. We can speculate, we can do this, and we can be lazy about checking whether it actually should have faulted because we're not going to actually release the values, so there's no vulnerability. Anyway, you can't find out what was in kernel memory. You can't find out what was there. Who cares whether it actually loaded it or not? It shouldn't matter, should it? That was their thinking when they designed these. And by being lazy about exactly when you check this, you can go faster because you can run things in parallel, and we don't actually have to run the check at the same time as loading it. We can run the check a little bit later, and it'll be fine.
I think, just to clarify, you sort of used the label kernel memory indexed by some offset. Of course, that's telling us you're explaining something. In reality, there could be some complicated expression where you're trying to get some value out of some bit of memory into W. And that complicated expression could be not deliberately, intentionally bad trying to read kernel memory, just is a complicated expression. Does somebody get wrong? And if it doesn't happen, then it doesn't matter.
Yeah.
So, in theory. And just happens to, the complicated expression happens to be offsetting into a kernel memory. Whoops. Okay.
Yeah, I mean, it's entirely possible that you speculatively might think that this would take you all the way up from user space into kernel memory, as John was saying. But if it doesn't run that branch, it never happened. Although it might speculatively execute it anyway. Okay, so this stuff would happen in normal execution of code, and it would speculatively load stuff from kernel memory, and then it would conclude, oh, I shouldn't have done that because v was not 0, and so it doesn't matter, and so that stuff would have been flushed. So the problem here is that this memory should not have been revealed. So we calculate something with it. We calculate something into X. We calculate something into Y. And we use Y to load something into Z from user memory. But none of that should have happened. And so long as we don't reveal the contents of X, Y, and Z, we're all good. OK. So what's going on here? Well, we can't fault here yet. So we don't take that path. OK. What do we do, though? So let me talk you through precisely what's going on here, because it's a little bit subtle. Okay. So we've got some value in W that we should not have been able to see. Okay. But we're being malicious, and we want to see it. Okay. So how do we see it? So the first thing we're going to do is we're going to AND W with 1. Okay. So So what this is going to do is x will be 0 if the first bit of w was 0, and x will be 1 if the first bit of w was 1. Okay? So the value of this depends on what was in this address. It's only a 0 or a 1. We then multiply it by 4096, and I'll get to why that in a second. And then we load from user memory into Z. So we're either loading in user memory 0 or user memory 4096. Okay? And then this stuff never happened because it was speculatively killed. But what you'll note is that we did load stuff into memory. Okay? Now remember how slow memory is. Memory, took 300 cycles to access. If it's in the cache, a few cycles to access. Very easy to tell whether it's in the cache or not, just by timing later on how long it takes to load user memory 0 and user memory 4096. They will be quite different. 300 cycles is a long time. If it's in the L1 cache, it'll only be for like 4 cycles. So it's not difficult to tell that difference. The timing is not, it's not a difficult timing attack to run. So what happens is we run this code, all this branch gets killed. It never happened. But this has side effects. Either user memory 0 is in the CPU cache or user memory 4096 is in the CPU cache, and then I write some code that follows on right after this to test which one of the two is fast. One of them will be fast. Whichever one is fast tells us what bit 0 of this is. And then you repeat it for bit 1 and bit 2 and bit 3 and bit 4 and so forth. And you can read out one bit at a time what the contents of kernel memory is. So that's a bit of a problem. So the reason you can do this is because of the side effect. Intel thought it was OK never to release these temporary variables, but there's a side effect that you can read. You can monitor whether something's in the cache. And if it's in the cache, it's going to be fast. If it's not in the cache, it's going to be slow. The reason for 4096, it puts these either 0 or 4096 on separate pages of virtual memory. And you want them on separate pages because actually some other stuff goes on in the background, like preloading of memory and things, but it won't preload across page boundaries. So this guarantees that nothing else messing on in the background will mess up your timing. So that's the meltdown vulnerability. It turns out that on modern Intel CPUs, you don't really even need the conditional. You can just run it and have the fault happen. And the fault happens sufficiently late in the pipeline, as in about there in the Pentium Pro pipeline, that you can have done quite a bit anyway before the fault happens. And then you can just handle the fault. You can trap the fault, because the OS will trap the fault for you and return execution to you, and then you can run your test. Turns out there's even another enhancement is there's some extensions on modern Intel CPUs for transactional memory, and you can use this to improve the performance further still. So in the end, the proof of concepts on the most recent Intel CPUs, you can read 500 kilobytes per second from kernel memory by using these tricks. It's just timing effects, but 0.5 megabyte per second is pretty interesting. OK, so what's affected? Basically, all modern Intel CPUs. Everything we use to protect operating system kernels from attacks for a long time, on all modern Intel CPUs are vulnerable. The most sophisticated ARM CPUs are also vulnerable, but most of them used in phones are not, to this particular one, but the two vulnerabilities I'll talk about later are. AMD claim not to be affected. There's a little bit of doubt on that claim, but let's take them at their word for now. They claim that this vulnerability doesn't affect them. So what should have happened? What really should have happened, and which is why we don't think AMD is affected, is that if they'd done the check here, they still can't fault there, but they could have stopped further subsequent speculative execution. Intel were obviously, in trying to get high speed out of their CPUs, they're being very lazy about when they bother to check the protection stuff. And so they carry on executing stuff without checking the protection on that page. They could have checked here. It would have been slightly slower. And if they'd done that, they wouldn't have had this problem, because you could have killed a speculative execution. Even though you can't fault, the fault would still happen down here. So they could have done this without major performance impact. Well, there would have been some. But they've obviously been pursuing speed over safety. OK, so what does this let you do? So what it lets you do from, for example, user space is to read kernel memory.
So if you have to do the check either in the speculative branch or in the real branch, It has to be done somewhere. So why does it give you a latency if you do it in a speculative process?
It's all about trying to get parallelism. So you want, if you can delay doing something and have it happen in parallel, then you can make it take less time. Yeah. If you've got to check the protection bit in the TLB, which is we'll talk about in a second, and then start the load, it adds an extra bit of delay to that pipeline. Whereas if you can start the load and then in parallel with that bother to go and check the protection bits, and only later on when you discover that it shouldn't have happened, cause a fault, then you can make that quicker. It's purely a performance optimization. But I think it's mostly that they simply didn't see the consequence. If they can make it faster and there doesn't appear to be a consequence from doing it. So Intel's response to this has basically been to say the CPUs perform as designed, which to me is a bit damning. It basically says your design is broken. But yeah, they never had in the spec that it shouldn't actually load stuff into the cache based on illegal memory accesses. Probably should have been. Anyway, so to go back to what the consequence of this is, with this, any user-space process can read kernel memory, which means if you don't trust all of your code, then you've got to have a bit of an issue here. It's even worse on 64-bit Linux. And the reason it's worse on 64-bit Linux is the virtual memory system I showed you is from a 32-bit Linux, but on 64-bit Linux, you've got so much address space that we can actually do some interesting performance optimization. We can take all of physical memory and directly map physical memory, all of it, every bit of physical memory in the CPU, into the virtual memory address space of the kernel, and then only map into the user space process the bit that they need. So this means that not only is kernel memory in the virtual memory address space for your process, but so is every other processor's memory in the virtual address space of process. So you can read that too. So one process running on your computer can read another process memory on your computer. So that means that we don't really have any memory protection anymore. And that's the basis for all of the isolation we do in operating systems. If you were assuming that your Docker containers provide some isolation from your thing running from other things on the same machine, nah, no isolation there. Hardware virtualization does actually seem to block this, but it takes the hardware virtualization extensions to do this. So here's a nice example which comes from the proof of concept webpage, courtesy of Michael Schwartz. So what this is here's your password manager that manages all your passwords. It's one process running on your machine. And here's a terminal. We're going to run another process in here. And we're going to use this process to monitor what's typed in that one. And this is screen video from them actually running this proof of concept. Come on, run. Oh. I can't actually see the tags on here to run it. There it is. Yeah. Play. Play. There we go. No, not play. How do I get that to play? There we go. Okay, so this, he's just typing his password in here, and look, it's appearing down here in a different process on the same machine. So if you don't think it has any impact, well, that's, I think, impact. Here's another one where so this process is basically going to be reading from another process's memory and output into a file, and it's using a separate thing here just to view the file. For this is basically reading an image from another processor's address space. Remember, it's just using timing side effects on the cache to be able to read this out of another process's memory. Yeah, of course, it's got to be a cat. So, yeah, protection. So that's where your operating system was meant to keep your processes apart and keep your kernel separate from your process. To be clear, this only lets you read memory. It doesn't let you modify it, but it lets you read pretty much any memory, and that's really, really bad. So why do the operating systems actually do this? Why do they map kernel memory into the process address space? The primary reason they do it is because there's you know a little bit more about how virtual memory works. I said this page table maps one to the other, but actually the page table is stored in memory as well. So to actually figure out where a page should be, we would have to go to the page table and walk through 3 levels of page table to be able to figure out where it would be. So each memory access would require 3 other memory accesses. And that would be really, 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 really slow. So there's a piece of fancy hardware called the TLB, or the this is basically it's in the hardware memory management unit of your CPU, and it's there to keep a cache of those mappings that you've used recently. And so if you try to access memory that's been loaded recently, there will be a TLB entry for that page, and it won't have to go to RAM to find out where to go in RAM. It will actually just be able to access it directly. If you try to load or store to an address in memory that's not cached in the TLB, then it's going to be slow. Okay. So another reason why your CPU manages to implement virtual memory fast is because the TLB actually has a reasonable cache. It's not huge. There's not a lot of page mappings cached in here, but there's enough to actually work. So what's the mitigation for this particular attack? The mitigation is not to have kernel memory in the address space of your process. Okay, so that's what Microsoft have done with Windows, and what Linux have done, and what other people are working on. They implement a mitigation called kernel page table isolation. And so, whereas before we had all the kernel memory in the virtual memory address space of our process, now we don't. We simply don't map those pages. So that means that if it's not in your address space, even though the CPU is broken, you can't read it. And so that mitigates this particular vulnerability. We still need something in the address space, because every time you do a system call, you need to start running some code there. Every time an interrupt happens, you need to run some code there. So you have these little tiny stubs, and what the job of those stubs is to switch the page table. So when you could do a system call with this mitigation enabled, you jump into the kernel, it starts running a little bit of code in the kernel. That code in the kernel switches from one page table, which doesn't have kernel memory mapped, to a second page table that does have kernel memory mapped. And that's safe. So we can no longer use this mitigation to read kernel memory or any other process memory. So what's the downside? The downside is to check when you change the page table, we have to flush the TLB. That's our cache of these mappings. So right after you've flushed the TLB, memory accesses are really slow, because we have to go to the actual page table in memory to look at the next step of the page table in memory to figure out where we should go in memory to actually load stuff from memory. And that's really slow. So the big performance hit now, every time you go into the kernel, we have to flush the TLB. So everything is slow when you go into the kernel, and it's slow when you come back from the kernel, which means that asking the operating system to do anything for you is much slower than it used to be. Also, every time the operating system processes an interrupt, it's much slower switching to the interrupt and much slower switching back to your process. So this performance hit, if your machine is doing a lot of I/O operations, if it's doing a lot of reads from disk, or it's doing a lot of network traffic, can be as much as 50%. That's, people care about optimizing 1 or 2% with CPUs. 50% hit from just working around this vulnerability. So the story's not quite so bad with the latest Intel CPUs from the last few years. And the reason is that their hardware is slightly smarter. They associate a thing called a process context ID with each of those TLB entries. And it will only use TLB entries if they have the right process context ID. So the upshot of this is that when you switch into the kernel, you can switch process context ID at the same time as you switch page table, and you don't have to flush the whole TLB. Just bits of it that were cached no longer accessible to you, so that's safe. When you switch back, hopefully some entries are still there, and it's not so slow. So this means that with this, if the OS uses it, and OS has never did until just this last couple of weeks, then you can mitigate some of that performance hit. It won't get rid of it completely, but it's a bit better than it was. So that's That's the Meltdown attack, and that's the mitigation for it. In terms of deployment, macOS distributed patches for High Sierra. As far as I know, they still haven't distributed patches for Sierra or El Capitan. So if you're running one of those, like I am on here, user processors can still read all your kernel memory. So that's not great. Microsoft patched everything from Windows 7, 8, and 10. If you look at their performance report from these patches, they say that the cost on Windows 7 is a lot higher than on Windows 8 or Windows 10. The reason is that they did some strange things on Windows 7, like font rendering happens in the kernel on Windows 7, which means that you do an awful lot of transitions to the kernel just to display a screen. So it's slow on that. In Linux, it's starting to ship now. It's shipping on x86. It's in the official, not in the official tree for ARM, but will be soon. There are Android patches available, but very few Android phones suffer from this particular vulnerability, so it's not a big deal there. Intel were very good at notifying Apple and Microsoft. They were reasonably good at notifying Linux, and they did not notify FreeBSD or OpenBSD or any of those people. So they got to know about this basically just coming into Christmas, which is exactly when you want to start rewriting your operating system. So FreeBSD, OpenBSD have not yet shipped patches for it. FreeBSD has patches, OpenBSD doesn't yet. So that's the Meltdown one.
Yeah, I think you might be thinking about this sitting looking at your phone or a laptop, but if you're thinking about you're running a bunch of applications in the cloud, and anyone else's process running on the same servers in the cloud can read all the memory of your process, so that's all of your Gmail, all of your Facebook, that any bad person can run this stuff. If Google and Microsoft Azure and people didn't patch all this stuff, then any of those services were wide open.
So they have deployed these mitigations. Google have, Microsoft have in Azure, Amazon have, and so forth. There are nice performance stats from various web services companies that show sudden 50% spike in their CPU usage on Azure when Amazon deployed these fixes. So suddenly your cost just went up by 50% if you happen to be running stuff in the cloud. Well, that's what it is.
Has there been any major exploits using this?
Sorry?
Has there been any major exploits using this? Public exploits?
Not that I know of. The proof of concepts have been out there for a couple of weeks now. There's some question as to whether the NSA knew about it. I think it's all speculation at the moment. It's possible that they did. Certainly there was enough information in the public about 2 years ago for them to have put 2 and 2 together and made 4 if they were thinking right. But given that it took the rest of the world until last summer, who knows? It's the sort of stuff they would be looking for, though.
If this has been an issue for so long, or like apparent, why is it taking so long for them to realise?
That's a really good question. I think it took the community to get to a level of maturity with side channel attacks in particular. So I've got 2 more vulnerabilities I'm going to talk about. They're along the same lines, but I think the reason it's taken them so long is partly because it's not obvious. I mean, it's the sort of thing that's really obvious with hindsight. And in advance, don't think so. So people started to play with side channel attacks probably about 5 or 6 years ago. They were looking, I don't know what hyperthreading is. So hyperthreading is this thing that modern high-end CPUs do, where to try and get better use of those parallel pipelines, they will run more than one thread, more than one process often, at the same time on the same CPU, and manage them as virtual processors. So you can actually be running your code on the same CPU at the same time as somebody else. Okay. And so people started to look at whether you could read something from one hyperthread to another hyperthread. And they proved that, for example, if you had exploit code running on the same CPU as someone crunching, say, RSA keys, you could actually read out what was going on with the RSA key computation. And so you need to be, that sort of side channel stuff was starting to bounce around a few years ago. About 2 years ago in the main operating system conference, people started to get bored of side channel attacks because there were so many side channel papers. People were discovering side channels. This cache timing is a side channel. Okay. But I don't think very many people understood the combination of side channels plus speculative execution plus the other things that you need in order to be able to put 2 and 2 together and actually figure out what's happening here. But the community as a whole had reached the point where we were sufficiently aware of side channels that you start to think, well, what else can we read? And eventually it was going to happen. But it took the community to get to that level of general understanding of what you can maybe be able to read out through these side channels. So, by the way, this being able to read this stuff through the cache, one thing you might say, well, how about they just unload those cache lines? Well, it turns out that actually there's other side channels you could use. For example, if as a result of that bit being 0 or 1, you decided to do a whole bunch of floating point operations, or alternatively a whole bunch of integer operations, you could then figure out whether the floating point pipeline was slow or the integer pipeline was slow right afterwards and read things out that way. So there's lots of things like that you could do which don't involve the cache at all, but involve other side effects that you can actually potentially monitor. It's just the cache one is so easy that it's by far the easiest one to read because the differences in timing between memory and cache is really big.
So one question about mitigations. So these
Okay.
mitigations are trying to still allow to access the cache in speculative execution?
Well, the problem is that CPUs have already shipped. So you don't get to change the CPUs out there. So the mitigations are, how do we avoid basically all of the operating system protection mechanisms that we use in the world being broken?
And that's something that you cannot touch.
You can't change the hardware. You can change firmware on some CPUs, and some of the stuff I'm going to talk about later has some changes to firmware. Okay, so Spectre, there are two Spectre vulnerabilities. Spectre 1 is very similar in principle to what I've just shown you. It turns out this one's actually very hard to mitigate, but why it's hard is a bit more subtle. Okay, so this is basically another protection check that you can skip. Okay, so with a little chunk of C code, we've got an array A that we're supposed to be able to read anything from array A, but we're not supposed to be able to read past the end of array A. Okay, and we've got another array B which we can do whatever we want with. Okay, and so we've got a little chunk of code here, and so this little chunk of code, there's a bounds check in this chunk of code. And this bounds check says that if the offset, which comes from some untrusted source, is less than the length of this array, then we can read it. And if it doesn't, then you can't read it. So where do you get this sort of code? You get this sort of code all the time. If, for example, this sort of code is in the JavaScript interpreter in your web browser, and it prevents JavaScript reading stuff that it shouldn't read. Okay? That little chunk of code should look pretty similar to what I've just shown you. Okay? This is basically the same thing I showed you for Meltdown. The difference here is we're not trying to read kernel memory. We're just trying to read beyond the end of where we should read within our own memory. So if this test is false, then we shouldn't run this. But you know how this works. It gets to here and it says, I don't know whether this test is true or false. Why don't we run it anyway? And so speculative execution will run this code, even if offset is greater than length. Run this, we leak some memory via the cache in the same way we did for Meltdown, and we've managed to read beyond the end of the array. So that's all this one is. It's basically the same thing as Meltdown, except for rather than being a hardware-enforced check, it's a software-enforced check. It turns out that makes it much more painful, but harder to use. Okay. So how do you use this? The first way of using it is you look at some victim code and you want to find some case that's in there which does something that looks something like this, that leaks information. It's unlikely you'll find it. It's not a very common thing. The people who have done proof of concepts for this have not generally stumbled across that, but maybe there's some code that you can find that looks like that. The more likely one is you use just-in-time compiled code. So the language engine inserts bounds checks. For example, JavaScript inserts bounds checks so that your untrusted JavaScript that you get on every time you load an ad from a web page or whatever, we try and sandbox that so it can't read your bank details from the other tab. Spectre just lets you bypass them, walk straight past those bounds checks. So the Google proof of concept code for this uses a thing called eBPF, which is a kernel packet filter just-in-time compiler that's in the operating system in Linux that lets you compile up little bits of code to hook certain packets that match certain filters and pass them up to your code. Okay. So because this has a JIT in the kernel, they can read kernel memory using this one as well. The Microsoft vulnerability team came up with a different proof of concept of the same vulnerability, which uses JavaScript. And you can put this JavaScript on a malicious web page, and you can read anything from the browser's memory. So you can read the passwords that are in the browser's memory. You can read the other web pages that the user has been browsing and things like that. So that's not really good. When JavaScript can just read anything and bypass all the checks in the browser, despite all the efforts that everybody's gone to over the years, we've got a bit of a problem there. So what's affected? This one's worse. All modern Intel CPUs, all modern AMD CPUs, and pretty much most modern ARM CPUs. So yes, your phone is vulnerable to this one. So what else? For you guys who have been playing with Intel's Secure Enclave stuff, SGX, it's meant to allow you to process secure stuff in your CPU. It uses encrypted memory, and stuff that's in the enclave is protected from stuff outside the enclave and vice versa. This walked right past that too. So yeah, SGX provides no protection then against the Spectre vulnerability either. There's proof of concept code here. So with the other one, with Meltdown, it requires basically a single fix in one place. You need to fix how virtual memory works. Ideally, you fix the hardware, but at least you want to fix how virtual memory works, and you can fix this. So what's the recommendation for this? This is difficult. Intel's recommendation is you put what they call a serializing instruction, an instruction like lfence, before any bounds check. So you have to go and read all of your code, figure out any possible bounds check that might be security important, and put an lfence before it. So not only does this give a performance hit from every time you do that, you've got to be really careful to put lfence every place you need it. Otherwise, this is easily bypassed. But you mustn't put it where it's not needed, because otherwise your stuff goes really slow. So you can't just go through and for every random if statement put an lfence, because you're going to really suck in terms of performance. So this one's really hard. ARM's recommendation is basically similar to Intel. There's got a compiler built in that's now shipping and so forth. AMD has been a bit vague on how to do this, but likely the mitigation will be the same as Intel because it's basically the same problem. This stuff's hard. Getting it right is hard. You may have noticed that there's been multiple different updates of your web browser. It doesn't matter which web browser you use because they've all been updated a lot in the last few weeks. The web browser have been trying to make this less exploitable. So the first thing that they did is they reduced the precision of time. Your JavaScript in your browser now gets much worse time precision than it used to. That makes it harder to use these side channel attacks. Second thing is that it turns out that there's multiple ways to measure time, and one of the ways to measure time is to run some code in a tight loop and find out how many times it goes around the loop. And if you have a way to communicate that, so you've got one process that's running around writing into a shared buffer as it increments, and the other process just reads that out. The other process or the other thread has a really nice time source. In JavaScript, there was a way you could do that using a thing called shared array buffers. So they've just prohibited that. It's like, gone, banned, tough. Broke a bunch of websites, tough. It's just too big a vulnerability, this. So these workarounds have been deployed in all the major browsers, pretty much simultaneously. Safari deployed it, Chrome deployed it, Firefox deployed it, Microsoft Edge deployed it. It's pretty clear that the browser vendors had spent a bunch of time beforehand talking about what to do, so that none of them could claim a performance win from this. This is sufficiently important that none of them wanted to be the standout. This is a mitigation. It isn't really a cure. It just makes it harder. Unless you break time so badly that nobody wants to use your JavaScript engine, then you're probably not going to completely cure this. The WebKit folks have been going through trying to rewrite their JavaScript engine. I'll come back in a second. Yeah? So what they've been doing is trying to find ways to substitute for those kind of bounds checks. So it turns out that CPUs don't speculate on bit masking. you can't come up with a sensible answer for whether it would or would not mask. So whereas before they would have tests like if the index is past the end of the array, then fail. Now they're doing things like array to data and then masking against a mask. And so long as your arrays are powers of 2 in size, this lets you prevent access outside of the bounds rather than preventing it this way. You can actually just say, okay, that will always be in bounds because it's forced to be by the AND. And so they've been going through and trying to rewrite code in all their JavaScript engines to avoid using tests like this, which are everywhere. They've also got some other things. This isn't the only vulnerability from this. There's other stuff too. So they're doing things like pointer poisoning, which basically involves storing encrypted pointers rather than pointers in the clear and doing maths on stuff like that. And I'm not even going to talk about that because it's too complicated. So you had a question?
Yes, I wonder if it's complicated to explain why JavaScript requires time and disabling it helps.
JavaScript requires time because tons of things in your browser are done on timers. So JavaScript, if you've got lots of different things running, often you'll trigger a lot of code in a web application based off timer events. And you want them to happen in a particular order, but you want them to happen very fast. And so, but you don't particularly want to have them happening off the main JavaScript thread because you want that to go off and do something else. And as JavaScript isn't really multi-threaded, then timers let you separate things. So one of the main ways you get things to happen in web apps is you set a timer for like a couple of microseconds in the future and let it go off. Having the ability to measure time is useful for that sort of thing. It's also useful if suppose you're doing a game and you want to render at a certain frame rate, okay? The question is, should I display my frame yet? But I need to know how much time's gone past before I can display the frame and things like that. So there's loads of cases where JavaScript needs access to time. What they've done is to make it so that you can only get access to the nearest 20 microseconds, which isn't actually a bad clock, but it's enough that they think it mostly mitigates these timing attacks. I'm actually not convinced. I think it probably needs to be a little bit coarser than that. But that's what they've done. Sorry, yeah.
And why does that help attackers with Spectre 1? Why would the time help?
Because they need to be able to do this cache timing. They need to be able to use the side effects of cache timing.
Yes.
And you need to be able to run it from JavaScript if your attack is in JavaScript. So you need to be able to tell which of these two memory references was fast. Well, if you can't read accurately, it's more difficult to tell. In actual fact, if you do the same thing multiple times, statistically, one of them will come out fast more often than the other, even with 20 microseconds granularity. So you can almost certainly launch a statistical attack against this, even with these mitigations.
Can't we check for malicious codes because they seem to have very consistent structure? This type of attacks seem to have very consistent structure. They have to check for cache timings and all these things. Can't you check for malicious codes?
You might be able to. I don't honestly know. If you see something that's doing an awful lot of access to timers, you might say, that looks a bit weird. Because that's what you need to do to get these side channels to work. There's a lot of access to calling what's the current time. The question is, does a lot of code do that? I don't know. I'm not a browser vendor. Probably some does, but most won't. You might have some false positives from certain JavaScripts that you would class as malicious when it was actually a game or something. But yeah, you might be able to detect it, but you would have to run for a little while before you actually have the potential to detect it. The question is, can you detect it before it's already leaked information? I don't know. It's still very early days with all of these.
It's a nice project would be to go out and do a data science over lots of JavaScript programs and see if you could work out the machine learning vulnerability warning system.
I mean, you can bet that people are trying all of this because these things are so far-reaching and so important to everyone that if there's a possible way of detecting this stuff, there'll be somebody working on it, I'm pretty sure. I heard somebody looking for, not this one, but Spectre 2, looking for a statistical, can we detect whether somebody's trying to exploit it? That one turns out that there are side effects work both directions. And so it's possible, more easy to detect. So this brings us to the third one. if you're not tired yet. So the first two are simple. This one's more. This one is nuts. The first two just let you read memory you shouldn't read. This one is a little more subtle. So this one that goes by the name of branch target injection. Okay. So the first thing is that let's assume that we can figure out where in memory a process or the kernel is stored. Operating systems these days load things into a randomized location in memory to try and avoid various other types of attacks. It's known as address space layout randomization. Let's just assume, for the sake of argument for now, that you know where the process you want to attack is. Okay. What Spectre 2 lets you do is to cause their process to execute any code you choose in its own address space. Yeah? And this is not a software bug. There's nothing wrong with the code you're attacking. It is perfect, and you can still cause it to execute any random place in its own address space. That's nuts. I mean, you can cause it to jump to some place and start running code there. So the basic idea here is the victim code has some kind of an indirect branch. So this is a jump to a location where the location is loaded from memory. Where do you use that? Well, it comes up all the time in all sorts of code. I mean, it's, if you, your operating system, for example, in a system call uses a jump table to make it jump to the right place and things like that. So there's very common to do that. C++, it's all over the place. So what you do is you figure out where that particular jump is in your victim's code, and we're going to make them jump somewhere else. So you flush the cache, and there's ways you can do to force the cache flush by basically rapidly accessing things. So that the location of the jump, as in where it's going to jump to, is not in the cache anymore. Okay. So now, when they get to that instruction, you've got about 100 cycles where the CPU will speculatively execute before it figures out where it really should have been. Okay. So CPUs will speculatively execute based on these jump targets. And what Spectre 2 lets us do is to poison the branch prediction. So instead of it jumping to where it thinks you're probably going to calculate to jump to, it jumps wherever you want it to. And so then you use the same sort of cache side channel effects to figure out what the hell the code did when it got there. But you can make it go anywhere in the process, which is pretty crazy. I mean, code with no bugs, and you can make it jump somewhere random. So what's going on here? We need to know a little bit, and I'm going to keep this pretty high level, about what's going on with branch prediction in modern CPUs. So this is sort of the Intel Haswell terminology, but basically the core has a thing called a branch target buffer. And the branch target buffer stores information about the branches that your code took. And so for each jump instruction in your code, it stores the target address, as in where you jumped to, and where you were jumping from. So it's storing that mapping of where I'm going from, where I'm going to. And that's stored in hardware in this branch target buffer. Now,
so by jumping, you mean go to instructions in the
yeah, exactly. I mean, jump is like assembly for basically go to. But go to is that kind of go to some location where the location is computed, not a static location. So that sort of stuff is used all the time. I mean, it's what your code compiles down to a lot of the time. So if the branch target buffer actually totally stored the source address and the target address and stored those unambiguously and so forth, there wouldn't be a problem here. But it doesn't. They took some shortcuts in how to do this. And they took shortcuts to minimize silicon and make it go fast. So what it does is, instead of storing the whole address, it only stores information about the lower 31 bits of our 64-bit address. And it folds together those lowest 31 bits using an XOR function. It's kind of a hash function. And so what this means is that multiple jump locations in the code will alias to the same buffer location that stores where you're going to go to. Can you see where this is going? Yeah. So indirect branch prediction, when you've got jump to the value of some register, is just a little bit harder than that. It's not just a simple, do I go that way or that way? It can jump to a computed location. Okay. So the branch history buffer on a Intel Haswell CPU stores the last 29 jump targets. But like this, it only stores part of the source address. So it only stores the lowest 32 bits of the jump target because it assumes that the upper 32 bits of the address are going to be the same as where you're jumping from, which lets you jump plus or minus 2 gigabytes. And then it basically uses a fairly crude hash of the lower 20 bits of the branch address. And it shares this history buffer. This is the nutty thing. It shares the history between all the hyperthreads on the same core. So multiple source addresses are aliased onto the same thing in the history buffer, and that's shared between different processors, which means that I can pollute the history buffer of another process, which means it's now going to mispredict, if I do this correctly, where that code will jump, and I can persuade it to jump where I wanted to jump instead of where they wanted to jump. So this is the slightly more detailed outline. I'll just sort of roughly lead you through it. You can look at detail later if you want. So you find the address of where you'd like to jump to in their code. What you're looking for is some bit of code in their process which, if you run it, will reveal something interesting to you. But it can be anywhere in the process. It doesn't actually even have to be a legal instruction. You can jump into some potential data and interpret it as instructions and do that. But it needs to have some observable side effect that you can observe through the CPU cache or something like that. So the Google proof of concept one inserts code using eBPF in the same way we did for the other Spectre one. So now you want to find the source address of an indirect jump in their code that you want to pollute that jump. So ideally, a jump that you can cause to happen. So in the kernel, you can make a system call, and then there'll be a jump in the kernel that will definitely happen. And so if we can pollute that particular jump, then we can make bad stuff happen. So now we make many, many indirect jumps using a hyperthread that's on the same core as our victim process. And what we use is a branch source address, as in when our interrupt happened, it's the address of that jump instruction aliases to the same place as the jump instruction we want to hit. And we use a destination address that has the same lower 32 bits as the gadget we want them to jump to. We flush the cache, forcing out the actual legitimate jump target, so that it'll take a long time to load that in from RAM again. And then we make a call that triggers that indirect branch. And what will the CPU do? Well, it will get a cache miss on the indirect jump. The branch predictor will try to figure out where it would have gone. It will load in from the branch history buffer the stuff that we've stuck there. And it will jump to where you told it to. And it will run code there until the legit jump target loads back in from RAM, which can be 300 cycles. Eventually, the CPU realizes its mistake, goes, oops, I shouldn't have done that, flushes the pipeline and pretends it never happened. But the side effects are still visible in the same way for the previous two. So this one's nuts. We can, it's not just reading memory. We can actually cause it to do stuff for us and then observe the side effect of what it did, which is really nasty. It turns out that, of course, to do this, we need to know what the addresses where their code is, because we need to know where the source and destination addresses of those jumps are. It turns out, actually, you can use Spectre to defeat that too, because we can basically try to exploit ourselves and figure out which things are fast and which things are not fast in terms of the branches, and we can use that to read out information from the branch history buffer. And if we call a system call a lot of times to load up the branch history buffer, and then we read out which of our jumps are fast, we know where they were, and we can read out information that way. So you can use this to defeat the address space layout randomization as well, which is kind of cool. So summary, this one's not that easy to deploy, but your ability to run arbitrary code in the victim's process is really powerful. Again, what's affected? Pretty much everything. Mitigating this one is not all that easy. What we need to do is somehow disable speculative execution of indirect branches, but given that happens a lot, that's going to hit performance. What's it going to hit worst? Probably languages like C++. Because what happens in C++, here's a little chunk of C++. We've got some base class with a virtual function here. We've got a derived class based on that base class. And so when we create a new version of this derived class and store it here, and then we call that function on it, how does it know whether to execute that or that? Well, the way C++ works is there's a virtual a vtable for every class instance, which stores the pointers to whether it's this function or this function. And so every time you do a method invocation in C++, when it's a virtual function, it will do an indirect branch. And if we prevent speculation of those, then suddenly the main thing you use to build C++ programs is really slow, which is not good. So what do we do? Not necessarily everything needs to have needs for you to disable speculative execution of branches, but certainly for anything important like the kernel, the hypervisor, etc., you need to. How are we going to disable speculation of indirect branches on CPUs that have already shipped? The CPU will just do this, so we have to somehow find a way to avoid it happening, to be safe again. There's two approaches that are taken. The first one is firmware updates, plus kernel support for the firmware updates. And so if you've been deploying firmware updates on machines, that's what's going on here. The second one is a really cool little technique called a retpooling, which I'll explain briefly. But so on newer Intel CPUs, Intel have released firmware updates, and they basically, if you go to your hardware vendor, they should ship you new firmware that will update the CPU, and then the operating system can use these updated calls that the CPU provides. The most important one is a thing called indirect branch restricted speculation, which if you update your firmware, and then the kernel can check for it, and it can use this to basically kill indirect branch prediction across, basically within the entire kernel. Or there's another version of it which you can turn it on and it will prevent it from everything, and everything will work quite a lot slower as a result. These are going to be performance hits. So turn this on or off as you see fit. Older CPUs, though, they can't fix it in firmware. And that's where things get weird. So if we can't fix it in the firmware, and we can't fix it in the CPU, where can we fix it? Well, how about the compiler? So we need to avoid generating any indirect jumps in code, all code.
But if you're a malicious compiler, then you can just make it executable and ship that.
Yep. So don't download binaries, or download them from a trusted place, but then that's probably a good thing anyway. So what we need, though, is something to replace these indirect jumps, because we still need to be able to do them. But we said that even on existing shipping hardware will not do speculative execution across the indirect branch. So what we want is a sequence that's going to replace the contents of jump to some register location. So this is a little tiny code fragment, which is called a retpooling, and it does this. So we start here, and the idea is we're going to use this chunk of assembly in place of this, wherever the compiler generates code. Okay. So the first thing it does is it's going to call setup target. Now that's a call to a static address. So there's no branch prediction vulnerability there. It will just jump to here. Okay. And we can't pollute that one. So what happens when you do that? Two things happen. That's the return address. This is a call, so we're going to be able to return from a call. Okay. So the return address is here. So what your CPU will do when you make a call like that is to push the return address onto the stack. But because the stack's in RAM, it's slow, and it wants the return to be fast. So the CPU also has this little internal cache, which it uses for return addresses. And this one turns out to be very hard to poison. I wouldn't say it's impossible, but it's certainly hard to poison. So it not only puts it on the stack, but it also adds it to its return stack prediction buffer. Okay, so now we go down here, and we overwrite the return address on the stack with where we actually want to jump to. Okay, so now when we return, it's going to go here instead of here. Except it won't, because it won't actually have the version that's on the stack yet, because that's on the stack and that's slow. So what happens is when it returns, it'll return to the version from its return prediction buffer instead of the version from the stack and start speculating. But we want to prevent speculation. So we return to here, because that's what was in that buffer. That's what got set up. And then we've got a little trap here. There's a little speculative execution trap, which captures it and stops it being there. And it will run around that loop until we finally figure out what was on the stack. And then, once we get the return address from the stack, makes it through the pipeline, finally we unwind the speculation, we go where we should have gone, and we jump over here, wherever we meant to go. So this is a thing called a new word as of 2 weeks ago, called a reppoline, which is a replacement for a jump instruction that captures speculative execution, doesn't let it go and do any damage. And so this is now implemented in LLVM and in GCC. You can compile code, and you should compile code, such as your kernel, with a flag to basically avoid doing any of these indirect branches. Implement this construct instead of all of that stuff. You also need, of course, to compile all of your dynamic libraries and everything else that you link against for this to be safe. Otherwise, you've still got problems. Google claimed this gives you about a 5 to 10% performance hit. That's this one, in addition to the other performance hits you might have taken. So on new Intel CPUs, you're probably better to use the firmware updates and enable this restricted speculation mode. On older CPUs, you don't get a choice. They've already shipped. We've still got to keep running them. So this is a mitigation that works for that. So mitigations for this one. Generally speaking, this is a complete solution if you recompile everything. So this is pretty good. For Meltdown, I think we've got a complete mitigation at the moment if you're willing to take the performance hit, which can be non-negligible. Performance costs are not trivial. This one, I think we're going to be living with for a long time. It's really hard to make sure that we've really sandboxed code within code. Our assumptions that we could do that are no longer valid. I think there's going to be a lot of work over the next few years on static analysis to detect when this is likely to be a problem and figure out where you should put L-fence and things like that. But I think it's going to be an issue for a long time. So these fixes are happening, but they're not really complete. For future hardware, if I were to speculate, I expect Meltdown will be fixed because it's really an Intel bug, and it should never have happened. And I think the next generation of hardware from Intel will definitely not do this one. Spectre, I think hardware fixes for Spectre 2 are pretty likely. For example, I don't think there's any reason why you should be sharing the branch history buffer between hyperthreads. You could maintain separate copies of it at the expense of burning some silicon to do it. Hardware fixes for Spectre 1, though, seem actually really hard. And I don't think there's any really great solution there. There's a massive fuss over the weekend on the Linux kernel mailing list because it looks like Intel are not really wanting to actually prevent all of these things in future CPUs. They're like, well, maybe performance hit is so big that actually we'll like to look good on benchmarks, and then we will not. And the problem is this pushes a lot of work onto the operating system to try and make sure that it figures out precisely what set of vulnerabilities this particular CPU has and then puts the right workarounds in place. It all gets really hard. So here's you can read that yourself. This is basically Linus Torvalds ranting about the patches, and it basically seems to imply that Intel are really not on the ball when it comes to trying to properly mitigate these things. Or that even something even more subtle perhaps, that he basically seems to be implying that these are not the right set of fixes, which might mean there's another vulnerability that Intel know about and that isn't public yet, that patches are going in which are worse than you would need to deal with the current mitigations. Who knows? I certainly don't. But anyway, it's not great. I mean, this affects basically everything we run code on pretty much, except low-end phones, and even those are vulnerable to some of them. So what about the future? Is it? We only know of these three, but I will bet that there are others. Certainly willing to bet you a beer that another one is found before the end of the year. I don't know in which. Maybe some of the return stuff will turn out to be vulnerable after all, with the right prompting. It's a really good question whether future hardware can be both fast and safe. The Spectre version 1 vulnerabilities are pretty hard to work around. I mean, you really have to disable speculative execution in places that the hardware cannot know whether it matters or not. And so that one is very difficult to work around. And I think we're going to be dealing with the fallout for that one for a long time, because I can't see that there's any simple solution to it. Meltdown should be gone with the next generation of hardware. Whether it is will depend on how long it takes Intel to ship new hardware. Spectre 2, we can work around that one, but it's should really be gone. But again, will probably take longer to mitigate. For Spectre 1, I don't see how we're going to prevent that one. Now, I'm not a hardware designer, so I may just be missing stuff, but it feels like the CPU needs to know stuff that it can't know to be able to mitigate that one completely. So anyway, that's these vulnerabilities. They're kind of interesting. We've certainly never seen anything like this before in terms of all of the main hardware vendors discovering simultaneously that stuff they've been doing for a long time is no longer safe to do. And the performance hit from working around them in terms of complexity is very significant. In terms of actual performance, depends what you're doing. One of my colleagues was measuring on Windows copying from one SSD to another, and he said there was a 60% slowdown because of, mostly because of the meltdown mitigation. So some of these slowdowns can be really quite significant. Depends on what you're doing as to how slow things really are. Anyway, this is pretty intense as seminars go. There's lots of things you need to know to be able to put the pieces together. I hope I haven't completely lost you. And I've still got another 15 minutes or so if you want to ask more questions, but if you're not completely like glazed over.
Hi, I have two questions. One is I'm curious why you haven't upgraded to High Sierra.
Because I have some software on here that doesn't work on High Sierra, which is really annoying that Apple haven't shipped that fix. My other two machines I have upgraded, but this one I haven't.
And the second one is what can we as users do? For example, even if we reinstall the machine and disable JavaScript and reinstall software, would that work?
I think if you're running on, say, Apple or Windows, your OS vendor has done a lot for you. Apple and Microsoft have been very good at shipping fixes. And the most important thing there is actually just apply what they've shipped. That will at least mitigate Meltdown and go a long way towards mitigating Spectre version 2. The browser vendors have done their best so far to mitigate them, but I bet they have a lot more fixes ship out over the next year as they try to prevent exploitable code constructs, for example, in the JavaScript interpreter. As a normal user, it's really hard because you have to know a ton of stuff to know what might be vulnerable. And there's no simple solution here. And to try to figure out, is my code going to be exploitable? Well, not that easy to know. So if you're willing to take the performance hit, and it depends on whether you're processing sensitive information. So suppose you're doing you've got a bunch of compute happening in the cloud. Should I recompile everything on my machine with reppoline and things like that? If you're handling sensitive data, yes. I don't think there's any dispute on that. If what you are doing is actually just doing a massive amount of computation of protein folding or something like that, and the threat surface is not severe, then no, don't deploy this stuff, because you'll take a big performance hit from doing it, and there's no need if you don't have a high threat surface. But if you're handling untrusted code or untrusted data, you really want to be aware of where the risks lie. But it isn't a simple, quick, soundbite answer. I don't have an answer for you there. And the problem is that to understand the threat surface here, you have to know more than most CS graduates know, let alone most normal users. So,
do you know if any of the antivirus companies or browser companies as such are releasing tools to flag possibly?
Oh, antivirus, that's a good side story. Loads of the antivirus vendors, it turns out, hook into the kernel in ways which are slightly dodgy. And it turns out that the kernel page table isolation breaks them. So if you want to break your antivirus, then fix your operating system. It's like, it was not previously known just how many of these did interesting, weird hooks into the kernel. So Yeah, there's a whole interaction between antivirus software, what they're trying to do, versus the things that we're trying to protect against these things. Yeah, but a whole bunch of antivirus software broke along the way. In terms of, will antivirus vendors be able to spot this? Antivirus is really a primitive tool. I mean, it relies on being able to spot something that's already been identified for the most part.
Yeah, but like you said, putting an else fence everywhere is going to be very difficult. So if it's possible that someone fishes out some of the at least false positives, then we can just go and check and just determine which are true positives.
So what would it check for, I guess, is the question. I mean, you can check whether the OS has been patched and flag that the OS has not been patched. That would be a useful thing to flag for. But it really ought to be your OS vendor that alerts you to those sort of things. If you're running an application software that's not been patched, maybe antivirus software can spot this version of your web browser is out of date, but again, it really ought to be that you're running up-to-date versions of your web browser. It's not really the antivirus vendor's problem. So I think the main story is if you're running code that handles data, especially just-in-time compile stuff like JavaScript, from an untrusted source, you really need to keep that code up to date because everybody who's handling that kind of code, JavaScript, etc., are doing their best to protect you. But if you don't update, then you're going to be out of luck, aren't you? Yeah, if you don't update your web browser and you're running JavaScript, I'm pretty sure that there'll be some malicious ads out there that will manage to read out stuff from your machine. It seems very unlikely there won't be, because it's just too easy to exploit, even this particular one. Antivirus, I'm not a big believer in antivirus software. I think it tends to really deal with things after the problem has already been there.
They did a lot of work into making CPUs fully verified and so forth. And they discovered this bug about the division in Intel CPUs a few years back, and that was in the design stage. Is it simply that this is side channel attacks and timing is difficult to do in theorem provers and logic and so forth? Why is it that this didn't get detected?
I think it's two things. First of all, side channel attacks are hard, just fundamentally fairly hard. And secondly, I think Intel not just Intel, ARM and AMD basically didn't really view it as being their problem. It should have been, but getting rid of all possible side channels is really hard. And so there's been,
So I guess the question is,
I mean, functionally, there's nothing wrong with these CPUs. Functionally, they do as designed. They are correct according to the model. The model is wrong. But modeling side channels is much harder than modeling functional blocks, because this is not a functional block.
do you know if the current provers and verifiers for CPUs, are they able to look at timing and side channel attacks and so forth?
I have
It's just
no
that-
idea.
okay.
I'm sorry. It's well outside of my area of expertise. Anybody know? No. I would imagine it's much harder. As I say, the cache one is the one that all these examples use, but the cache is not the only side channel. It's the easiest one to use, but it's not the only side channel. There are others, for example, as I said, stuffing the execution pipeline and figuring out which arithmetic operations change performance, things like that. In general, the concept of hyperthreads seems to me to be looking extremely risky compared to what it used to look, but it's a big performance win for CPU vendors. If you can run two threads at roughly the same time on the same CPU and get parallelism out of it, then great, nearly a performance doubling. For me, if I was running very sensitive stuff on a machine, I would probably disable hyperthreading at this point. I just don't trust it enough, and it gives too much control over an attacker to pin stuff on the same core as me at the same time as me. But it's a performance trade-off. I mean, they've had these amazing performance improvements over the last, if you look at sort of CPU clock speeds, until about 2000, CPU clock speeds got faster and faster every year. And around 2000, they stopped being able to make them faster. And since then, CPUs have continued to get faster and faster every year because they've got smarter and smarter about doing parallelism. And doing parallelism is all about keeping that pipeline full. And we're starting to realize that a lot of the tricks we used to make CPUs keep getting faster are riskier than we thought. That's the issue. Now, how do you avoid possible side channels in those? I don't know. Maybe we just have to tolerate that if If you really care about security for that particular machine, that particular application, you're going to take a performance hit. And I can't see there's much alternative there.
I think that could be a trend of effectively slower and slower CPU speed because we are discovering new vulnerabilities? Or do you think that's just a one-time event and things will go back to their normal growth speed?
That's a very good question. I'm probably not the right person to answer it because I'm not a CPU designer, but I'll try and speculate anyway. I think that what we're discovering here is definitely this sort of big discovery is a one-time event. But what the impact of that will be is hard to foresee. It looks at the moment like Intel want to keep going the same way they have been and just let people shut things down when they need to. The problem is that knowing when you need to is hard. And so that approach, I think, is not going to win them any friends in the long run. Now, if you are running compute in an environment where there just isn't a threat model, that's fine, but most of those aren't. So I think that they're going to have to start to be serious about side channel attacks. This is probably the tip of the iceberg. These particular ones are ones which were found relatively fast once people started to look for. Turning off speculative execution would be a huge performance hit. I don't think we're going to go back to CPUs that don't do speculative execution. I think what they will try to do is get better at unwinding the side effects. So you could, for example, unwind cache loads that had happened as a result of speculative execution. And that would make it harder to use a side channel. You could separate the branch history buffers for different threads so that they can't affect each other. And that would make it harder for one to influence the other. It might make it impossible for one to influence the other. You could argue that this particular process is doing sensitive stuff, and therefore it must be the only hyperthread running on your CPU, which makes it harder for other stuff to interact with it. And these are things you could do. But I think we've got too used to machines being fast to really completely roll back. And where it lands, I'm not sufficiently well placed to be able to foresee. But I don't think we're going to stop doing speculative execution because the win is too big. If you don't do it, it's so hard to use all the parallel instruction pipelines through a CPU. So I think we're going to have to try and figure out how to mitigate it. And what we'll find out is that the mitigations were incomplete. And other side channel effects will crop up over the... Even when we got new hardware that is less vulnerable, people will still find ways to read information out of them. That's my guess. It's not a story I want to tell. It's much nicer if I can assume fundamentally that the hardware is secure and then I only have to worry about software bugs. That's hard enough. Okay.
Okay. Well, let's thank Mark very much for a